Potential energy and kinetic energy. So the units are joules. So already you should get the sense that it is related to work in a way. And so potential energy is a stored energy as the result of work done on an object. So there are many kinds of potential energy. For example, if I lift an object, I do work to lift that object, the higher the object is, the more damage it could do, the higher the potential energy it has, the more potential it has for doing something. Other forms of potential energy would be a spring. If I stretch it or if I compress it, I have to do work in order to stretch or compress it. And there's this potential energy that's built up into it. If I let it go, boom, it could really do a certain amount of work that I could harness. A bowstring that you're pulling, a log that can burn. So the food that we eat, when we look at it, we say it has a certain amount of calories in it. That's potential energy. That's the potential energy that we have that if I ate it would enable me to do work. So we'll concentrate on potential energy here as a unit as a result of height. So lifting something to a high object, bringing it down. The other ones, the spring and the bowstring, you would encounter in other physics courses. And the log that can burn, that's going to be concentrated on in chemistry next year. So potential energy, the units of potential energy are MGH, and that should look familiar to you. MGH is also the force times displacement that we use for work. So there you can see that the amount of work that I put in is the potential energy that is given to the object. So I can have a greater potential energy if I have a higher mass, or I take my object to a higher height, or both. So an elephant on a high dive has a higher potential energy than a raisin on a high dive because it has greater mass. Or a brick at the top of the building has higher potential energy than the brick at ankle height, right? So it's the same mass there, but because the brick at the top of the building is much higher than my ankle is to the ground, then it's going to have higher potential energy. If one dropped on your foot, the brick from the top of the building would definitely do more damage to you than one that dropped from ankle height. Similarly, if a raisin fell from a high dive onto you, it wouldn't do nearly as much damage as if an elephant fell from a high dive onto you. So that's potential energy. Nothing's happening yet, but it has the ability to do work or damage to you. The other energy that we're going to look at is kinetic energy. So kinetic, as its name suggests, means that it's movement. So it's the energy that results from the object's motion. And the formula for that is 1/2 mv squared. So if my mass is higher, I will have a higher kinetic energy. If my velocity is higher, I will also have a higher kinetic energy. So a speeding car has higher kinetic energy, can do more damage if it slams into you than a slow moving car. That's the velocity is higher. And a marshmallow has less kinetic energy than a bowling ball. Even if I throw a marshmallow at you, it's not going to do nearly as much damage as if I throw a bowling ball at you with the same velocity. So here are some examples of calculations. So what is the change in potential energy as a brick with a mass of 2 kilograms drops from 8 meters to 1 meters? So I can either look at this as the change in my potential energy, as in what was my initial potential energy, what was my final potential energy, and how much energy was lost. So if that was the case, I'm going to be using MGH initial. So that's 2 times 10 times 8, which is 160 joules. And then my final would be mg times final height. So 2 times 10 times 1 is 20 joules. So I went from 160 to 20 joules. I lost, because remember it's always final minus initial, I lost 140 joules worth of potential energy. I could also do that by just doing mg times delta H. And in that case, I would have to remember that my delta H would have to be 1 minus 8. So that would be 2 times 10 times 1 minus 8, which would still be negative 140 joules. So whichever makes sense to you. And here's an example of kinetic energy. So I can look at it as what's the kinetic energy I have right there, kind of like momentum. So what's the kinetic energy of a 2,000 kilogram vehicle moving at a velocity of 30 meters per second? So I plug that into my 1/2 mv squared, and remember that squared only applies to the v. So it always helps to put it in parentheses by itself. So 30 squared is 900 times 2,000 divided by half is going to be equal to 900,000 joules, a huge amount. I could also look at it in terms of change in kinetic energy. So what's the change in kinetic energy required to increase the velocity of a 2,000 kilogram car from 10 meters per second to 35 meters per second? So initially I have a kinetic energy of 100,000 joules. That's 1/2 times 2,000 times 10 squared. And I want to take it to 35 meters per second. So I plug that into my final. So that's 1/2 times 2,000, which is my mass. And my velocity now is 35, so it's 35 squared. So it becomes 1,225,000 joules. So the amount that I have to increase the kinetic energy is going to be equal to 1,125,000 joules, which is a huge amount of kinetic energy. The reason why the kinetic energy is going to increase so much more is that you'll notice that the velocity is squared. So whatever I do to the velocity is going to have an exponential effect on my kinetic energy. That's why when sports, anytime you're doing sports or anything, oftentimes we'll try and increase the velocity of something before we increase the mass of something. Increase your bat speed, increase your punching speed, increase your golf swing, that type of thing. You're trying to increase the velocity because that's going to have an exponential effect on the kinetic energy that your object has when it leaves.